Hi everyone, in this video we will go over section 15.1, which is double integrals over rectangles. Recall what a regular integral does. When you have a function y equals f of x, integrating that function from points a to b on the interval a to b amounts to finding the area under the curve. And what it really is we take these really small segments and we add all these rectangles, or add the areas of all these rectangles together, and that is a regular integral as we know it. Now, extending this integral to higher dimension, what we get is a double integral, which gives us the volume under a certain surface. So for example, suppose we have a surface z equals f of x comma y here, and we have our xyz coordinate plane. If we take the projection of this on the xy plane, we get this region R, right? So what we do now is we take this region R, and if we split this region R into a grid, so instead of working on an interval, we are now working on this region R, which is defined as the product of these intervals here. And if we focus on any one of these and move it up to the surface, it will correspond to this particular region. And using the same analogous definition, if we add up all the volumes, we get the volume under the given surface, which is z equals f of x comma y. So pretty much similar to what we have before, this small change can be thought of as dx and dy, and dx times dy is the area of this sliver, and when we multiply this by the average height, this height is your f of xy function, and we take the double integral, which is to say, we haven't defined this yet, but it is a double summation. So it's summation over two indices. The formal definition is the double integral of f over region R is the limit as m and n go to infinity of this double summation of this function times the delta A. So basically, just as in regular integration, we're going to break this down into a bunch of finer and finer grids. And eventually, if this function is greater than or equal to 0, then the volume is then the integral is equivalent to the volume, just as the case with area. If it's negative, then we can always flip it to get the volume. Let's look at an example similar to what you have done in Calc 1. Estimate the volume of the solid above this region 0, 2 cross 0, 2, and below this paraboloid z equals 16 minus x squared minus 2y squared. Divide R into 4 equal squares and choose the upper right corner as the sample point for each. Okay, so we need these both of these information. First of all, we need the 4 equal squares, so we know what the grid size is, and choose the upper right corner so we know which one of it corresponds to the actual height. Right, so first of all, I'll start with the region R. It's a 0, 2, 0, 2. Breaking this into 4 equal squares will give me squares of size following. and these will be the coordinates of these points. And based on the choice, the upper right corner, we're looking at these points as the samples for each height. The delta A, the area for each is 1 by 1, so it's just 1. And the sample points for each f1 comma 2 is going to be whatever we get when we plug this in. So 16 minus 1 squared minus 2 times 2 squared, which is 16 minus 1 minus 8, which is 7. 2 is 16 minus 2 squared minus 2 times 2 squared. 16 minus 4 minus 8 is 4. 1 is 16 minus 1 squared minus 2 times 1 squared, which is 16 minus 1 minus 2, that is 13. And 2 is 16 minus 2 squared minus 2 times 1 squared. 16 minus 4 minus 2 is 10. And so if we add them all up, we get 2334, which is the approximate volume. So that's the approximate volume. But what is really going on, it's a little bit hard to draw this, but what we have is we have a surface where z, that's z equals 16 on the z-axis, and that's the surface. We're trying to find the volume that it has if we were to extend this all the way down to the xy plane. But instead of finding the exact volume that it has, what we have instead done is we have basically taken a projection of this into the xy plane. So we have here a 2 and another 1 and a 1 projection, and for each of these we have kind of stacked these boxes up here wherever they meet. Sorry, so it's the upper right corner. Let's see if we x is, yeah, so that's going to be the upper right corner. So we take this height of this box, meets over here. We take this height of this box, we take this height of this box. I mean, they should all be, they should look nicer. Drawing not very accurate here. And the upper height, so somewhere in this vicinity, gives me this box. So what is 34 is the area of all of these, the boxes all together. So they will be an underestimation. So just as with the Riemann sum, you can have an underestimation or a overestimation depending on how well that has been done. So which means if you take, say, lower left or lower right or upper left, you would get different values. You can also do the same thing with a midpoint. So try it out. Try the problem above, but using a midpoint, and this is going to be extra credit that you can send by email. Let's look at another example which says use midpoint rule, m equals n equals 2. So we have a 2 by 2 grid again, and estimate this integral. So we are interpreting this as a volume question where x is between 0 and 2 and y is between 1 and 2. So here our region is slightly shifted in a sense that it's not around the origin anymore. So x is between 0 and 2, but y is between 1 and 2. So here we have our region 1, 2, and it's split again into 4 parts. So I will write down the coordinates of each of these. This is 2, 1, This is 1 comma 1 and this is 0 comma 1, and I have a 2 comma 1.5. Oh, actually, sorry, so it's, anyways, we need it, so let me put it 2 2 1 2 2 0 0 1.5, and this point is going to be 1 1.5. Now because we are using a midpoint, we need to find the midpoint for each of these region. So let me do that in a different color here. So this midpoint is going to be halfway between, for x value, halfway between 0 and 1. So this is going to be 0.5, but it's halfway between 1.5 and 2, so it's 1.75. Similarly, this one will have the same y coordinate, so 1.75, because it's at the same height, but it's 1 ahead, so it's going to be 1.5. Next we have, this will have the same x value, so 0.5, but it will be at 1.25. And lastly, let's keep this blue, will be at 1.25, but now shifted to 1.5. And again, I'm not going to complete this, but the area of each square here is 1 by 0.5, so it's 0.5. And then for each of these, you can find 0.5 minus 3 times 1.75 squared, 1.5 minus 3 times 1.75 squared, 0.5 minus 3 times 1.25 squared, 1.5 minus 3 times 1.25 squared. Get all of these, add them up, and then multiply by this 0.5, because the area of each of the base, which will give us the volume of the big solid, is 0.5. Okay, so I'm gonna pause this video here, and in the next video we will go over how to evaluate the iterated integrals without doing these kind of rectangle things, just as the transition from doing Riemann sums in regular single integrals to using the integration results for finding antiderivatives directly. So that's it for this particular video.